Morning, everybody. What a dreary day. I know at least one other person experienced inversion of stereochemistry. I did with my umbrella coming over. I think Gabriel did too. Anybody else have a problem with their umbrella going from R to S? It happens. It happens. I got a big whiff of some wind, and man, it really took off. So I want to, before we get into the stuff today, of course it's not chapter 2. These are some slides that I use when I teach 255, Organic Chemistry 255, and I like them, so we're going to do them. But I want to go through some reactions just to keep us in practice. So how would we convert this alkene into this alcohol? What are we going to have to add across the carbon-carbon double bond? Essentially water. Right? And so we know that there are two ways to do that. We can use water and catalytic acid, right? Or we can do the hydroboration oxidation sequence. Which one do I need here? What kind of alcohol do I have? It's a primary, that's right. Right? So the OH is on the least substituted carbon. So is that water and acid, or is that hydroboration oxidation? No, not that one. So it's got to be hydroboration oxidation, right? So this is the hydroboration oxidation sequence. Sodium hydroxide. I'm just going to write hydroxide, and this pen's giving me a little bit of a fit, so we'll switch. Okay. Now, what would we use on the second one? We would use the water and acid, right? So we'd use water and sulfuric acid, small amount of it, catalytic amount of it, and that would give us that. So the top one here, these are called anti-Markovnikov alcohols because the hydrogen actually went to the most substituted carbon. Down here, these are called Markovnikov alcohols because the hydrogen went to the least substituted carbon, or the carbon with the most hydrogen. So one follows Markovnikov's rule, one does not. Okay? What would I use in the third reaction? HCl. Yeah, we would use hydrogen chloride. I'm adding a hydrogen and chlorine across the carbon-carbon double bond. So I just simply need HCl, and that will work. Okay? How would we do this reaction? So we just produced this alcohol by taking this alkene, adding water, sulfuric acid to get this alcohol. How could I take that alcohol now and convert it into a ketone? Jones reagent. Yes, Jones reagent will do this. I need an oxidant. Right? And so we would use Jones reagent. Anybody remember what Jones reagent is? CR, so it's chromium, trioxide, sulfuric acid, and water. It's a mixture of those three things. They're in a specific ratio, but we don't go through that in the class. Kind of an orange color, right? I showed you a picture of what it looks like. So, in theory, we've learned this reaction. We've learned this reaction. We have never learned the reaction of taking this alkene to this ketone, but you all have every tool in your toolbox to do it. You just know that you have to add water across it first to get an alcohol, and then take the alcohol and make the ketone. Okay? So, theoretically, we can take alkenes and make ketones out of them. We just have to go through the intermediate of an alcohol. Okay? So, these become kind of road maps, if you will. Right? Once you know a series of reactions, you can use a series of reactions to do whatever you want to do. All right. Last one. How would you take benzene and make this quaternary ammonium salt? I think I heard it. Couldn't hear you.
Do you break the aromatic ring?
Well, that's part of the mechanism. In the mechanism, we will do that. How should we be thinking about this? You're thinking about it from benzene to quaternary ammonium salt. We've never talked about that directly. Excuse me. So we really need to think about this backwards, don't we? How do we make quaternary ammonium salts? We make quaternary ammonium salts from amines, oops, 2, and alkyl halides. I need 3 of them there, so just to keep everything balanced. I know it has to be iodide because of the iodine in there, right? Do I have the amine yet? I don't. Can I make the amine directly from benzene? Directly in one step? Not in one step. Right? But I can make them from what? How can I make that aniline? I can make it from the nitro compound, right? So I can take nitrobenzene. And I can make aniline. I can take aniline and I can make the quaternary ammonium salt. I don't have nitrobenzene yet, but I can make it straight from benzene, right? So I've gotten to where I started from. So the first step then would be to take benzene and convert it to nitrobenzene, right? What reagent would I use for that? Pardon? Nitric acid. And? Well, technically, it kind of is a catalyst, but we don't say it's catalytic. But what is it?
Sulfuric acid.
Sulfuric acid, yeah. It's a mixture of nitric and sulfuric acids. The sulfuric acid doesn't get consumed, so you're technically correct, but we don't use it in catalytic quantities. Usually it's a 50-50 mix of nitric and sulfuric acids. So it's really not catalytic in terms of its quantity. How would I convert the nitro into the amino? How would I replace those oxygens with hydrogen? Is that an oxidation reaction or a reduction reaction? It is a reduction. We're adding hydrogens, not oxygens, right? So you learned at least 3 ways to do that. Just give me one.
Iron and HCl.
Iron and HCl would work just fine, right? You could go to Lowe's, get a little bit of iron and hydrochloric acid. You can do that, make that just fine. That's one way to do it. What was the second way to do it? Tin. We can use tin instead of iron, so we can use tin and HCl. That would have been perfectly fine. And then there's a third way to do it that's a little bit overkill in terms of its expense, but it'll work. And what is that?
Catalytic conversion.
Catalytic hydrogenation. Yep. So palladium or platinum along with hydrogen gas. That'll work. But this is perfectly fine. We make the amine. Now all I need to do is take that and react it with 3 equivalents of iodomethane, and I can get that. Usually what I would say there is we're going to use an excess of it. We would make a quaternary ammonium salt, and we would be good to go. So, if you're up in my laboratory, and I have you do one of these reactions, how do you know if it worked? Do you just trust that it should? How do you do that? How do we know if a reaction works? How do I know if I took this alkene and I made an alcohol? How would I know? Test it somehow. Yeah. What kind of tests can we do? What kind of tests might you think about that we could do to determine this? I did a demonstration the other day with some bromine. There could be a way to test that, right? How would that work? Huh? Go Go ahead and say it. Yeah, I'm going to look at the color, right? Yeah. So if this reaction completely goes to the product, I won't have any alkene left, right? And if I add a little bromine, the color should stay. If this reaction didn't go, the color would dissipate, wouldn't it? That's one way to do it. Does that really tell me whether or not I've got the product that I've got? It just tells me I don't have the starting material anymore, right? It's not, it is a test for something, but it's not necessarily conclusive, right? For those of you in forensics, conclusive tests are very important. It's not enough to say X if X isn't conclusive, right? You're gonna, if you all are in forensic science, one of these days you all are going to get called to the stand for your work. And you've got to be confident that what you said is true. Not only is somebody's life on the line, perhaps, being incarcerated or whatever, but also your reputation, right? Once you lose your reputation, it is hard to get it back. So guard it. It's your most valuable asset. More valuable than your home, more valuable than any car you'll ever have, is your reputation. So, as a scientist, we have to be sure about what we say when we say it, right? We have to be very clear. So the bromine test is something that we could do, but all you can really say is that this is no longer present. Okay, but that doesn't necessarily mean you made that alcohol. Maybe you made this alcohol. Maybe you made that alcohol. We don't really know, do we? Maybe you made something totally different. Maybe you picked up the wrong reagent model that also reacted with the alkene. Right? You just don't know. What would you call it going from this to this, other than hydration? What's another word that you might use? On the left, I have an alkene. On the right, I have an alcohol. What are those two things in general? Remember, we had a list of them at the beginning of the semester, and I said you need to memorize certain what? Functional groups. Yeah, right? So we have an alkene functional group, and I have an alcohol functional group. So maybe I need a test that can test for more than just one functional group, right? The test that Alyssa brought up was about the functional group for the alkene, and that's all it would really tell us anything about. But I did a functional group transformation. I took an alkene and I transformed it into an alcohol, right? So I need something that will tell me something about this functional group, something about this functional group. And that's what we're going to talk about today. Infrared spectroscopy. We call it IR. You all have probably heard the word IR before. Where have you heard it? Okay, you do use it in your lab, and that's going to be in the context we're talking about it here. But in just general, before you ever walked into a lab, you might have heard the term IR or infrared before. Where might you have heard that?
Infrared scanners.
Infrared scanners, yeah, you all probably got familiar with that during COVID, right? You'd walk up to the scanner and temperature 98 point, you know, whatever, and you were free to go. Yeah, so temperature. Where else have you heard about infrared? It is part of the electromagnetic spectrum. We'll talk about that. Where else have you heard about infrared? Any of you like the remote to the TV? It's got the little dot-looking thing in the front of it. That's an infrared transmitter. It's using infrared radiation from the electromagnetic spectrum to change your television's channel. Okay? Where else? Anybody like fast food? Right? Why is it fast? Is it fast because they prepare it all at the moment you order it, or is it fast because they prepare it ahead of time? They kind of prepare it ahead of time, right? They've got things cooking and all this stuff. How do they keep your hamburger warm before you order it? Heaters. What are those heaters? Some restaurants you'll see these big bright lights, right? You know what they call those? Those are called infrared lights. They transmit infrared radiation and it keeps your food warm, okay? So we can actually use infrared radiation to heat our food, to change our television channels. We can use infrared radiation to tell what our temperature is. without having to stick a thermometer down our throat. We can use infrared to also determine what kind of functional groups we have in a molecule. Okay? It's a very easy test to do. You've probably done it in your lab, not hard to do at all. The equipment looks like this. It's actually a complicated piece of equipment. Well, that's not terribly complicated. Looks complicated. Okay? Most of it I leave for the physicists to explain to you. Okay? All you're worried about is the fact that we're going to take infrared radiation and we're going to put it through a sample and we're going to see how it absorbs that infrared radiation. And that infrared radiation is going to tell us something about what functional groups we have. IR spectroscopy is very good at telling me what types of functional groups I have. It is not so good at telling me how those functional groups are connected together. So if I did an IR on this reaction or on this reaction, they would look very similar because both of them have an OH. But nonetheless, I'd be able to tell that the reaction had gone. Okay? We'll learn more about how we can determine which one we would get in the next lecture. Okay? So, let's talk a little bit about the electromagnetic spectrum. You've got radio waves over here. You've got cosmic and X-ray and gamma rays over there. We want to stay away from X-rays and cosmic rays because they're harmful. They're ionizing radiation. They tear your molecules apart. Cosmic radiation that you all get exposed to every day, and you get exposed to it more when you get up in an airplane, it will actually nick your DNA. It can cause cancer. It's the cancer-causing radiation. Okay? Radio waves. Right, for those of you who still listen to the radio, you're in your car, you turn on the radio, local station, 99.4, whatever. This is what you're listening to, right? That's how they transmit that. And there's a lot of stuff in between. And what we're going to focus on is this stuff kind of around here in the middle, in this infrared, okay? Don't worry so much about these wavelengths. What you need to know is very short wavelength, very long wavelength. And so infrared is kind of towards the longer wavelength. You know what a wavelength is. You know how long it is from crest to crest in a wave. Okay? And so very high energy, much lower energy as you go higher and higher in wavelength. So the higher the wavelength, the lower the energy, right? So very high energy, very low energy, relatively speaking. Okay? But right here in the infrared region, this is where things start to do what's called vibration and rotation. The molecules that we have built with our model kit, if you believe this model of benzene, for example, you would think that it is just that these atoms are always this distance apart, and that that's what it looks like. But in reality, these models do a very good job of telling us how things are connected and whether or not, if they're flat or not. But it doesn't do a very good job of telling us how they wiggle. Molecules aren't static. They bend, they move, they wiggle, they waggle, they zig, they zag. Okay? They do all sorts of things. And sometimes when they wiggle, their dipole changes. Okay? And when that dipole changes, they can absorb infrared radiation. This is how your infrared heaters work. Your infrared heaters don't work because it's heat coming, it's heating you up. That's what it's doing. It's making your molecules vibrate and wiggle and waggle and do all sorts of weird little dances. Okay? And we can measure that using this thing called an infrared spectrometer. Okay? So, in the infrared region, we're going to talk about vibrations. The microwave really starts to talk about rotations. You all know what microwaves are, right? You have probably one at home, in your dorm room, wherever you are. What do you use it for? You use it to cook food. Well, if you've ever stuck just a paper towel in a microwave and accidentally turned it on and pulled it out, you notice it didn't heat up. Microwaves work because it takes water in the food and it vibrates it very, very fast. And when you vibrate something very, very fast, it creates friction. And when it creates friction, it creates heat. You're literally cooking food from the inside out, not the outside in, with a microwave. Okay? So we can use a lot of this type of radiation to determine what's going on in our molecule. Okay? So, basically what you do is to get an infrared spectrum, you will take a sample, you'll put it in the infrared spectrometer. There's many ways you can put it in the spectrometer. Okay? Modern instruments are different than the instruments I learned on, but they all got to put a sample in. It's usually a liquid that you introduce. You can do solids, you can do gases as well, but most people typically do liquids. And you shoot the radiation through the sample. So I know what radiation is going into my sample, and I measure what is coming out. If less is coming out than what I put in, what does that mean? The sample had to have absorbed it. And it will absorb it at its functional group. Okay? And infrared radiation has many wavelengths, and functional groups don't all absorb at the same frequency or same wavelength. Okay? However you want to do it. We call these wave numbers in infrared. Okay? And a wave number is reciprocal centimeters is the unit, but all I care that you worry about right now is that it's just wave number. Okay? And so wave numbers, it goes from about 4,000 to 600 or 500, something like that. And the spectrum is broken up, okay? And so what happens is you will get a spectrum that looks something like this. There are other ways to show it, but this is typically what it looks like. So you see on the y-axis, how did we label the y-axis? What does it say up there? What's that word? Transmittance. It's not absorption. They're inversely related. Okay? So if I'm at 100% transmittance, what does that mean? Zero absorption. So if something's close to 100, it means it's not absorbing any of that radiation. But you'll start to see these peaks, or these troughs. What are those? Those are absorptions. That's where the transmittance is going down. So something is absorbing that radiation at about, well, let's just call that 3,500. Okay, halfway between 3,000 and 4,000. Something's being absorbed there. A little something's being absorbed just about 2,100 or 2,200. And then something here is being absorbed around, I don't know what that is, about 1,600. These are peaks. When I look at that, I know what these functional groups are. And you will too. Okay? I know that's a carbonyl, that's probably an alkyne, and that's an alcohol. Okay? You'll learn this. Okay? It absorbs radiation characteristic of the function group. And what's really magical about this is it doesn't really matter too much. I'm telling you a little bit of a fib here. It doesn't matter too much how the functional groups are connected within the molecule. They all absorb about the same place. So a carbonyl, a C double bond O, is going to be roughly in that region. An alcohol is going to roughly be in that region. There might be little shifts, but I know by just looking at that spectrum what it is. Okay? So, you all are going to have to figure this out on your own. No, I'm kidding. You all will be able to figure this out very easily because there are regions of the spectrum where these functional groups absorb. And your book has tables that will help you out with that. And we'll talk a little bit through that as well. Okay? So, has anybody ever heard of Hooke's Law before? Anybody had physics in high school? Hooke's Law tells us how a spring vibrates. And if you ever take a physics class, you'll probably do this experiment where you take a mass, you put it on a spring, and you measure the frequency that it bounces. And then you take another mass and you put on there and you measure the frequency with which it bounces. And what you find is that the mass matters. The more mass you put on, the more it can stretch the spring. That makes sense, doesn't it? Right? If I take a spring and I put a small mass on it, it's not going to stretch it as far, right? If I put a big mass on it, it's going to stretch it a lot, right? Is that true for all springs? Turns out it is, but the magnitude is different. So if I took a little spring like is in an ink pen, have you ever pulled one of those springs out? And I put a huge mass on it, what's it gonna do to that spring? It's gonna stretch it completely out, isn't it? But if I took your car spring, your front tire car spring, and I put that mass on, is it gonna stretch it all the way out? Probably not, because one spring is stiffer than the other. It's called a force constant, okay? And so that's called the stiffness of the spring, right? And so that's the equation for Hooke's law. You are not going to be responsible for solving Hooke's law. I'm not trying to scare you about it. What I want you to see is that the frequency of a spring is dependent on K, which is the stiffness of the spring, and the masses that are connecting the springs. Well, that's nothing more than a bond, right? The bond is a spring. It can, and again, these aren't good models, but imagine these atoms can spring. This atom has a mass. This atom has a mass. Masses are involved. And is what's stiffer, a double bond or a single bond? Well, a double bond would be stiffer. Why is that? Because it's got the single bond or the sigma bond, and it's got the pi bond. You're right that the pi bond is the weaker of the two bonds, but having two bonds stiffens it. So it's harder to stretch a double bond than it is to stretch a single. Well, I broke it, but a single bond.
Here's what I found.
Okay. So that's what you need to know. So double bonds are stiffer than single bonds. Triple bonds are stiffer than double bonds, and so on and so forth, okay? What two atoms are connected together determines the stiffness of the spring, okay? So the model here is that your bonds can be thought of as springs. They are not springs, you all know that, but they behave like springs, okay? So your molecules will actually vibrate, okay? And they can absorb energy in the infrared region, okay? All right. So, know what Hooke's law basically says. Do not worry about solving the math for Hooke's law, okay? It's not important in this class. All right. So, when you look at two atoms connected by a spring, you have a lower vibrational state where the two atoms are actually closer together. And then if the right amount of energy comes in for that system, it can absorb it. And when it absorbs it, it actually stretches. That's what absorption is. It's taking that energy and converting it into motion. Okay? Are you starting to see how this can heat up your food? It takes your food and it starts to move it faster, kind of like the microwave does. Except when it does this, it creates friction and heat. That's what keeps your hamburger warm. Okay? Okay, so that's how these infrared systems work. And we can measure that through the spectrometer. Okay? All right. Your book has a lot of detailed tables, and they're great. You will probably need them to answer some of your homework problems. You will not need those to answer any of my exam questions. What you need to memorize is this. You need to memorize this one chart. How many people thinks that looks complicated? Be honest. Okay, it's not. And I'm going to tell you why it's not. I'm going to teach you all the little tricks. Okay? There are three regions that you need to know about. There is the functional group region, there is the fingerprint region, and there is the aromatic region. A seasoned chemist needs to know all of them. You all only need to know one of them. What is it? It is the functional group region. Where does the functional group region start in terms of wave number? Right there. 1500. I would go lower to higher. Right? So it starts here. The first thing that you're going to do when I give you an infrared spectrum to look at is you're going to find 1500 and you're going to draw a line at 1500. You're going to literally take your pencil and draw a line at 1500. and you're going to ignore everything that is lower than 1500. There is a problem or two in the book where you will have to pay attention to the fingerprint region, but don't worry about it, okay? Use your tables. But on the exam, you're gonna ignore the fingerprint region. Now, turns out that nature is good to us, and all you have to remember, start at 1500 and then add 500. What's 500 plus 1500? 2000. So I come out here and I find 2000 and I draw another line. Everything between 1500 and 2000 is called the sp2 region. Anything that is sp2 hybridized is going to appear in that region. A C double bond O, a C double bond C, a C double bond N. They're going to all appear in that region, right? So I'm going to find alkenes here. I'm going to find carbonyls here, ketones, aldehydes, those types of things. Alkenes tend to be closer to 1500, whereas carbonyls tend to be closer to 1700. But guess what? If you don't see anything in here, if it's all up around 100%, you don't see any peaks, and my choices for you have carbonyls, you can cross them all out. It can't be that. Right? There's no absorptions there. Well, again, Mother Nature's good to us. We just add another 500. Now we're at 2500. We draw another line. This is called the SP region. This is where we're going to find anything that's SP hybridized. You're going to find carbon-carbon triple bonds. You're going to find carbon-nitrogen triple bonds. Anything that's SP hybridized is going to appear in that region. Okay? And then from 2500 to 4000 is what we call the hydrogen region. It's the more complicated region to interpret. Okay, but you're going to find carbon-hydrogen bonds, oxygen-hydrogen bonds, and nitrogen-hydrogen bonds in that region. Okay. So, I give you an IR spectrum. Where do we start? What do? We draw a line. Now where do we go? We move over 500 to 2000. What do? We draw a line. And what do we call that between those two lines? That is the sp2 region. It's easy to remember. The fingerprint region is really the sp3 region. It just goes sp3, sp2, sp hydrogen. That's all you got to remember. Okay? We're going to draw another line where? 2500. Yeah, and we're going to call that region between 2000 and 2500 the SP region. And then everything 2500 to 4000 is what region? That is the hydrogen region. That is right. So we're going to find all of our NHs, CHs, OHs, all of that kind of stuff in that region. Think we got that? All right. So, when you start to look at the different regions, things get a little more detailed. Okay. So if I look at the hydrogen regions, the CH bonds, you'll see that alkanes are between 3000 and 2850. You'll see that alkenes are between 3100 and 3000. And you'll see that alkynes are about, if they have a hydrogen on them, are around 3300. And remember, we go in higher wave numbers, we go this way. So I'm going to see alkanes, then alkenes, then alkynes. Okay? So I know to kind of start around 3000 to about 3300, and that's where I'm going to look for my hydrogens. Anything between 3000 and 2850, I know that that's going to be some type of hydrogen attached to an alkane. If I see things somewhere around 3100 to 3000, that's going to be an alkene. And around 3300, those are going to be the alkynes. Our carbon-carbon stretches, right? Where do you think that C, single bond C is going to appear? What region? Fingerprint. Yes. That's going to be in the fingerprint region. That's below 1500. Right? C single bond C doesn't tell you a whole lot because just about every organic molecule known to man has a bunch of CC bonds, right? And so it gets complicated. But look where we start to see the carbon-carbon double bond. That's in the sp2 region. And it's around 1600 to 1680. And the carbon-carbon triple bond is definitely in that sp region, right? So notice it takes more energy as we increase the force constant, right? The force constant's increasing because a triple bond is a stiffer spring than a double bond, and a double bond is a stiffer spring than a single bond, right? And so we can see that quite clearly in the infrared spectrum. Where would we expect a carbon-nitrogen single bond to appear? Fingerprint region. Where would we expect a carbon-nitrogen double bond to appear? sp2 region. Where would we expect the C triple bond N to appear? The sp region. Very good, right? But what you'll notice is that the shifts are a little different, right? So a carbon-carbon triple bond is 2100 to 2250, but a CN triple bond is going to be 2240 to 2260. There is some overlap, right? But they are slightly different, the regions, right? So again, increasing force constants. Your book has tables like this where you can actually look and see all of the details. So, you know, aldehydes are a little different than ketones. Ketones are a little different than esters, yada, yada, yada. On the exam, I am not going to give you anything that requires extreme fine detail. Your homework might. So you need to know how to use these charts. Okay? And it's a good practice for you to go through. For those of you in forensic science, you will do infrared spectroscopy at some point in your laboratories. It's a great way to identify functional groups, right? We know that cocaine is an amine. An amine is a functional group. If we don't have an amine functional group, it ain't cocaine. It might be a white powder. It might be something somebody was sniffing, but cocaine it cannot be, okay, because it's not an amine. All right? So you'll learn these types of techniques. Okay? So let's look at some real examples. And before I before I put up the spectrum, octane, where would you expect everything to be? What regions would we expect to see stuff? I'd expect to see things in the fingerprint region for the carbon-carbon single bonds. And I'd expect what else? I'd expect a lot of stuff in the hydrogen region. About where? Approximately. It's an alkane, right?
3,000.
Yeah, around 3,000. That's what I'm expecting. Am I expecting to see anything in the sp2 region? In the sp region? No. And so, in fact, that's what we see. That's exactly what we see. So if I come in and I draw my line, there's 1,500. All this is the fingerprint region. There's all the CC stuff going on, okay? But we're going to ignore that. That's 1,500. 1,500, there's 2,000. There's nothing there. 2,000 to 2,500, there's nothing there. But now all of a sudden I'm starting to see some stuff over here around 3,000. That's that CH stretching and bending and all the little different things that it can do, okay? That's what octane looks like. That's the IR spectrum of octane. Now, if I remove a couple of I'm removing a couple of carbons too, but I've gone from an alkane function group to an alkene function group. Now tell me what you expect to see. What do we expect? Do we expect that it's going to look identical to the one at top? They're both hydrocarbons. But the functional groups aren't the same, right? We're going to see some differences. What differences are we going to start to see? Where are we going to start to see some stuff appear? We're going to start to see some stuff in the sp2 region, which is where? Between where and where? Nope. Well, 2,000 is the top upper part. So where is the lower part? Yeah, so 1,500 to 2,000, right? You got to remember where we start. What else would we expect to see? Yeah, there'll be some stuff in the fingerprint, but we're going to ignore that. We're going to expect some differences in the hydrogen region. We're going to see stuff that looks similar because there's some alkane portions of it, right? But this alkene, notice we have some hydrogens on those carbons. So where are they going to appear? Are they going to appear closer to 4,000 or closer to 3,000? They move a little more towards 4,000, don't they? Towards that direction, right? So, and in fact, look what we see. Right, so there's the fingerprint region right there. So we're going to ignore all this. So there's 1,500, there's 2,000. Notice I've got something there, right? That's the carbon-carbon double bond stretch. All right, notice here around 3,000 again, I've got some of this stuff. But then notice this other peak that comes right here at about 3,100, 3,200, depending on how you want to look at it, right? That's these hydrogens that are on the sp2 hybridized carbons, okay? So we can clearly see that this is different, even though all we've done between these two, other than the difference in carbons, is take two hydrogens away and make an alkene, right? I'm starting to see stuff in that sp2 region, okay? Notice it doesn't go all the way down to the bottom, right? This is what we would call a moderate absorption. And it's because a carbon and a carbon have the same electronegativity, and when you stretch them, the dipole doesn't change much, so it doesn't absorb very strongly. Okay, you'll start to see some differences in how strong the absorptions are with different functional groups as well. And what do we think for hexyne? We're going to see something in the sp region. Yeah, we're no longer going to see anything in the sp2 region. What's the hydrogen region going to look like? Well, it's a terminal alkyne, so that hydrogen's going to be even further towards 4,000, right? So that's what we're going to see. So notice, there's 1,500. There's really nothing there. There's a little bit of something. Anybody know what that might be? I don't know. A little blip, right? 2,000, really nothing there. Between 2,000 and 2,500 in the sp region, there's a stretch. That's an alkyne. That's the carbon-carbon triple bond. There's my hydrogens for all of this stuff. And there's my hydrogen for my alkyne, the CH. Notice it's sharp. When I look at that, I know because of its shape and where it's at, that has to be an alkyne. It's a nice sharp peak. Okay? It's just characteristic of it. Okay? All three of these things are hydrocarbons. All three have different functional groups, and I can distinguish the functional groups very easily by looking at these different things. Now, if somebody just gave me this, could I tell you that it's got 6 carbons? I couldn't tell you that. That's a different type of spectroscopy that we'll learn about on Tuesday. Okay? But I know what the functional groups are. I know that that has to have an alkyne. I know that that one has to have an alkene, and I know that one is some type of alkane. That's what I know, right? So anytime you're given one of these spectra, draw your line at 1,500, draw your line at 2,000, label the regions. Use your process of elimination. If one of my choices said, or was drawn out where something was sp2 hybridized and you had the spectrum up at the top, you know that that can't be it. There's nothing sp2 hybridized in that molecule, right? So process of elimination is a good way to go here. All right? Let's look at a couple more molecules. Let's look at a couple of alcohols. So here's sec-butyl alcohol, or secondary butyl alcohol, or how else would we name that? 2-butanol. Yep, that is 2-butanol, right? This is what those spectra look like. OH stretches are very, very characteristic of alcohols. What can you tell me about the shape of that peak that is unique? It's, okay, kind of rounded. I call it parabolic, right? Throw in a math term, it looks like a parabola, right? It occurs around 3,400, and it's broad. Okay, it's distinctive. I know that's an alcohol just by looking at it. That is a characteristic alcohol absorption. Okay? And what you'll notice is that both of them have that. Okay? This one also has, of course, some sp2 hybridized hydrogen, or carbons that have hydrogen on them. So you're seeing hydrogens here, and you're seeing some hydrogens here for this, right? But also when you go here, so there's my 1500, there's a little C double bond C. It's kind of in the noise, but it's there. Aromatic rings do this because of the aromaticity. They don't absorb very strong, but they're sp2 hybridized. They are there. I look up here and I notice there's nothing in the sp2 region. There's nothing in the sp region, right? That has to be some kind of just regular alcohol. Do I know that it's 2-butanol just by looking at that spectrum? No. But I know it's an OH group attached to some type of alkane. That's what I know. Okay? All right. I think you all have a lab. Have you all done an infrared lab yet in lab? You should have an infrared lab. I don't know if Miss Autumn has scheduled one or not. I hope she did. But you got to be careful when you handle these samples because you don't want to contaminate them. You don't want to get water in them because guess what water looks like in the IR spectrum? It looks just like an alcohol, right? So you want to make sure your samples are dry and you've got to use special handling kind of techniques. You can do this through what we call thin films. You can do this by what are called Nugel moles. You can do this by what are called KBR discs. A lot of ways to do it, but today, when you go in and use an infrared spectrometer, it actually has what's called a diamond anvil. So it's got a diamond anvil on the top. You put your sample on it and you crush the sample on there if it's solid, or you cover it with a cup if it's a liquid. It's a little piece of diamond. It works really well. But those are fairly new instruments. Old instruments used these things called cells. And they were literally, the ones that I used when I was a postdoc anyway, we all had our own set of cells. They're actually made out of sodium chloride, potassium chloride, or silver chloride. They're salt cells. And they are these little wafers. They're about the size of a quarter. And they're about 3 times as thick. And it's just pure salt. It's been polished and ground, and you can see through it. Okay? They are highly polished salt cells. What do you think the problem with working with salt is? It dissolves in water. So when you're done running the experiment, you can't just go wash them off in the sink. They just dissolve. And each cell at that time, back in 2000, 2001, each cell was about $100 a piece. Very expensive salt. And if you dropped them, they broke. And so I went through several cells, okay? And what you'd do is you'd take a sodium chloride cell, you'd put your sample on it, you'd take another piece of sodium chloride and you would put them together and then you'd stick that in the spectrum. Yeah?
Did they also call them crystals by any chance?
I've never called them a crystal.
In my lab, we moved to diamonds, but we were working with crystals that you could not get wet, and we had like 3 of them broke. And
Yeah, it was probably sodium chloride or potassium
they're
chloride.
like $7,000 now, so.
Then it's not those.
Okay.
Some other material. Now silver chloride would be very expensive just because it's silver. Okay? But the reason that you use sodium chloride or potassium chloride or silver chloride is they don't absorb in the functional group region. There's no functional group to absorb. So we say it's transparent to the region that we're interested in. You don't want your cell absorbing a bunch of stuff. It complicates life, okay? All right, and so you would typically take, if you had a solid material, you would take that solid material and you would dissolve it in some kind of solvent. Typically we would use carbon tetrachloride or carbon disulfide or chloroform to do this, to make a solution that we could then get an IR spectrum of. And you would always run the IR spectrum of your solvent first, so that you could subtract it out of your spectrum. But it turns out that those solvents don't give strong IR absorptions because their dipoles don't change much. So they're not strong absorbers. Okay? So, knowing what we know, I want you all to get in groups. Okay? I really do. Get in groups. We're not doing this on our own. Okay? And I want you, yeah, I don't either. So I want you to work through each one of these problems. Take about 5 minutes apiece on it. You two gonna work together?
We go sleep and then I go down to C and H2. But all I did was this. Maybe.
All right, where do we start? We start at 1500, right? So let's draw a line at 1500. Right, we're going to draw a line there. We're going to ignore all of this. We're going to draw another line where? 2000 right there. Do we have anything between 2000 and 1500? Yeah, so we definitely have something that is sp2 hybridized. Based on that alone, what can I eliminate? Yeah, I can eliminate A. B, C, and D all have something that's sp2 hybridized though, right? So now we got to look a little more in depth. Right, so we go from 2,000 to 2,500, there's nothing there. And so 2,500, now we're going to have to look in the hydrogen region. Okay? Given all of that, what do you think is the likely solution? I'm hearing a lot of B's. I heard a C. It is B. B is a ketone. Ketones, the C double bond O absorbs very strongly. So you'll see this nice sharp peak. You would also see that for both of these others. So how do I know that this isn't the case? Notice a carboxylic acid has a carbonyl, so it would be there, but it also has an OH. So I would have expected to see something in the hydrogen region that looks similar to an alcohol. Not quite an alcohol, but similar to an alcohol. And we just don't see anything there. Also notice this has a nitrogen with two hydrogens, and all I see is alkane type CHs. I don't see any NHs. Okay? You would have looked at them, but we don't see any of those. So B is the best answer for this particular problem.
What would the peak of an NH look like?
It depends on the type of NH. If it's a single NH, it appears as a single peak. If it's an NH2, it actually has two peaks.
Okay.
We're not going to get into why. There's symmetrical stretching and asymmetrical stretching, but anyway, yeah. All right, 5 minutes.
sometimes break down.
Where do we start? Start at 1,500. I move over how many? And draw another line, right? So between 15, this never works on the TV screen. So between 1,500 and 2,000, this is the what region? SP2. Do we see anything there? We do. So can I eliminate anything based on that? I can eliminate B, can't I? There is nothing SP2 hybridized in B. Everything else has at least something that's SP2 hybridized, right? Okay. So we can eliminate B. Now we're going to take a step over again from 2,000 to 2,500 and draw a line. This region is what? SP. Is anything there? Yes. Can I eliminate anything based on that? I can eliminate D. D does not have anything SP3 hybridized, right? Or SP hybridized. It's got SP2 and SP3. So I can eliminate D. I just went from a 1 in 4 chance, if I have to guess, to a 1 in 2. If I'm at the casino and I've got 1 in 2 chances of winning, I'm putting my money on the table. Because I'm going to leave beating the house. Okay? If you play long enough, you'll win, right? 1 in 4 is not a very good odd. 1 in 2 is not bad, right? So we know it's not B. We know it's not D. So it's either got to be A or C. What is the difference between A and C that should be cluing you in? The extra oxygen could, if you're getting into the details. I won't deny it, but you'd have to be looking in your charts. But not looking at your charts, what's the telltale thing? What is the difference between these alkynes? Does that alkyne have a hydrogen on either of those carbons? But this one does, doesn't it? So the hydrogen should be obvious to us. Do we see a CH on an alkyne in the hydrogen region? Remember, we see sp3, sp2, sp. So alkane, alkene, alkyne. Do we see that? Do we see an extra set of hydrogens? Or an extra hydrogen? We do not. The answer is A. Right? If C was the right answer, you would have expected to see right around in here another peak. And we don't see that. Pardon? You would see it somewhere around here. Right? Because this is the hydrogens for the alkane part. And if we had seen something just kind of right in here, that would have been an alkene, and an alkyne would be somewhere around here. So you would have seen another peak. All right. Take 5 minutes. All right, where do we start? 1500. Always start at 1500, so right there, right, so it's, well, right there, so it's cutting through that one, so it's kind of, that's still gonna be the fingerprint region. And we go to where? 2000, and that's the what region? It's SP2. Do I see anything? So can I eliminate anything based on that? I can eliminate A, B, and D. So the answer has to be C. Notice the alcohol stretch. There's the alcohol. Whoop. Rats. Right, so there's the alcohol stretch. All right, last one. Which of these structures, or which structures is consistent with this IR spectrum? Take about 5 minutes. $1,100 would be in the fingerprint region, so we're going to ignore that. If that's hard, you can't really tell the number of carbons or anything like that. It's hard. Yep.
Okay, I have a question.
Yeah.
How do I like? So, do you start at the beginning of the so like do I start at CH3 or can I start at like any one that's different? So could I start at like carbon?
Again, what you want to focus on is just the functional groups. So find the functional groups and focus on those. Okay?
So you think this that's confusing. CH. So really just the back part, that's what I was, and then work on it.
Where do we start? Broken record, it's 1500. So we're going to start at 1500, we're going to ignore all this. From 1500 to 2000, that's the what region? SP2, do we have anything there? Yes, can I eliminate anything? No. From 2000 to 2500, that's the SP region. I don't really have anything that's clear there. and I don't have anything that's SP hybridized, so there's really nothing to worry about there. What is different about this spectrum from all the others? This is pretty broad, isn't it? Very broad. Kind of looks like an OH in that it's broad, but it's not just right here and looking parabolic, right? It looks like it overlaps the other hydrogen regions. This is what a carboxylic acid OH looks like. Okay, so the right answer is B. The OH of a carboxylic acid is very broad and gets in the way of all the other hydrogens. Okay? It's a very telltale sign. However, if you see this and you go carboxylic acid, you would also better see, dang it. You'd better see this. Because a carboxylic acid has both the OH and the C double bond O. Mhm.
How would you choose which also has an OH bond?
It does, but if it was just an OH, I would have expected that to look like a regular alcohol. I would have seen the hydrogens, very clearly here, and then I would have seen a parabolic OH. Yep. Yes, ma'am.
Can you explain that?
Well, technically, you're not incorrect, but you won't be able to determine that. It's very difficult to determine quantity of hydrogens or quantities of carbon from an IR spectrum. It's not impossible. Really, you're going to just have to look at functional groups. Okay? All right, everybody, have a great, yes, ma'am.
The line for the carbolic acid, is it always look like that? Can we know what's your hydrogen by that?
If it has that plus that. Because the carboxylic acid has the C double bond O and the OH. So you're going to have both of those things appear. If you just have this, it means something totally different. And usually it means that your sample's not prepared. You don't need to worry about that. All right, folks, I'll see you next week. Have a great weekend. We have finished chapter 10, so that should be a hint for Tuesday, okay?